model. Ah, you are recording, or?
Try to record, yes.
Yeah, so to that purpose, I developed the first model of annotation in the literature that is able to aggregate anaphoric judgments model, which we used to aggregate the interpretations collected by the phrase detectives game with a purpose. And as a result of that, we published the phrase detectives corpus, which stands as one of the largest crowdsourced corpora in NLP. And the corpus was also used in many of the research of my colleagues. Another role I had was to help inform the NLP community about best practices for annotation analysis, for assessing coding schemes, or for aggregating annotations to create corpora, or how to train machine learning models on multi-annotated corpora. And to that purpose, I co-authored a book, a number of conference publications, journal papers, co-organized a workshop, co-presented a tutorial, and finally, I was also responsible to help the team with machine learning expertise. It's mostly related to probability theory, and I had collaborations with many of my colleagues on various topics, from anaphora resolution to game with a purpose or learning with disagreement. Let's see, okay. So I'm going to give a brief description of the survey we published back in 2008 at TACL. This work came as a result of observing that many people still use simple heuristics to aggregate annotations, heuristics like majority voting, even though probabilistic models of annotation have been around ever since the 70s, and they have been shown to be much better at aggregating the judgments. I'm going to use this example of an annotation task in this talk for this paper. This is the recognizing textual entitlement task that Barbara also mentioned. I've included here the annotation patterns from the Snow et al. Data set. So these were Snow et al. Back in 2008. They annotated the RT corpus. And we can see here the annotation patterns. And what I wanted to show is that simple heuristics such as majority voting are not always right. And in this particular case, you can see, for example, that in 62 cases, 6 out of 10 coders said these are positive cases of textual entitlement, but 18 of those 62 cases, the experts concluded differently. The main issue with majority voting is its assumption that all coders have the same ability, and this is really not a plausible assumption to make when analyzing the annotations from different coders. Notice, however, that the correct interpretation is among the interpretations provided by the coders. We just need better tools than this simple heuristic to identify that. And it has been suggested that probabilistic models of annotation can be the right tools for this task. In simple terms, probabilistic model of annotation allow us to encode our assumptions about the annotation process, so how the coders and the items interact. And then these are assumptions are considered when at inference time, when the corpus labels are being estimated, when the labels are being distilled from noise. I decided to include probably the most widely known and used model of annotation in the literature. This is the David and Skeen model published back in '79. So this model assumes that every item has a true class, so one correct interpretation. And the prior probability for the true class is given by the prevalence of the true classes in the corpus. So going back to our RT example, the prior probability that a pair of sentences is a positive case of textual entitlement will be given by the prevalence of the positive cases of textual entitlement in the corpus. And the model also assumes that the coders annotate according to their annotation behavior relative to the true class of the items. So the annotation behavior of the coders is modeled in David and Skin with the help of a confusion matrix. And we have here some estimates of annotation behavior. Looking at the good annotator, for example, the confusion matrix, the rows in the confusion matrix describe the distribution that characterizes how the coders annotate when they encounter items of a certain true class. For example, the row on the top in the confusion matrix indicates how the coders annotate when they encounter negative cases of textual entilement. And the good annotator will have a large probability, 0.81, of correctly labeling a negative case of textual entilement. So that's his specificity. The sensitivity of the coder in that case is 0.76. So the probability of correctly identifying a positive case of textual entilement in that case. So the estimates from the main diagonal tell us, in a sense, the accuracy of the coder, and the estimates, the off-diagonal elements from their confusion matrix tell us the bias of the coders. If we look at the coders that are biased, for example, coder 88, we can see that irrespective of the true class of the items, they have a large probability of annotating with a negative label. And coder 65 has a large probability of annotating with a positive label, irrespective of the true class of the items. I included here the estimates of the ability of the coders that annotated the RTE data set. And in the left-hand side graphic, in the left graphic, we can see that the coders have varying specificities and sensitivities. And this really shows that they have a varying ability. I included this graphic in response to the assumption made by majority voting that all coders have the same ability. And in the graphic from the middle and from the right-hand side, we can see the sensitivity, the specificity and the sensitivity of the coders plotted against the gold estimates of these quantities. And the correlation is very high, indicating that the model does a good job at properly capturing the ability of the coders. One objective of the DALI project was to identify ambiguous cases in interpretation, and the concept related to ambiguity is the difficulty of the items. The model I described previously assumes that the coders condition on the true class of the items, they annotate independently, but anybody who has been involved in an annotation project has come across items that are quite easy to annotate, and also there are items that are more, that create more disagreement between the coders, that are not that easy to annotate. And I've given here 2 examples. In the first example, all the coders agree that's a positive case of textual entilement, but in the second example, the coders are split between positive and negative case of entilement. So Carpenter, back in 2008, recognized this effect and proposed a model that takes item difficulty into consideration. In their model, the probability of a coder being correct on an item is based on a subtractive relationship between their ability, alpha j there, and the difficulty of the item, theta I. And these parameters are expressed on the log-out scale. Negative estimates of the difficulty parameter will mean that the item is easy, because in this case, the accuracy of the coder goes up. So is increased, the easier the items, the larger the probability of correctness the coder has. And when the estimates of the parameter are positive, the item is considered to be difficult, because in this case, the accuracy of the coder will go down. So the harder the item, the lower the accuracy of the coder. Here I've included some estimates for the difficulty of the items from the RTE dataset. So these are the average difficulty of the items with different agreement patterns. I should better say with different disagreement patterns. And we can see that the difficulty estimates, nicely correlate with the way we perceive difficulty with respect to disagreement. That is, the more disagreement we observe on the items, the more difficult the items are on average, and the more agreement we observe, the easier the items are. Another interesting property this model has is that the difficulty estimates the difficulty estimates and the ability of the coders are on the same continuum, in the sense that they are directly relatable. So for the easiest items in the corpus, we can see that we need a coder of at least 0.18 ability to annotate them correctly better than random. Whereas for the most difficult items, we would need a coder of at least 0.69 ability to correctly annotate those items. Another work I would like to describe in this presentation is the one regarding the anaphoric model of annotation I mentioned in the beginning of this talk. I'm going to start with a description of the anaphoric annotation task. So here, the coders are asked to mark mentions with anaphoric information, whether they introduce new entities into the discourse, in which case they have to say that that's a discuss new mention, or whether mentions refer to previously introduced entities, so to discuss old entities. And in case a mention refers to a previously introduced entity, they need to specify that entity. And to specify it, they will have to, one way they can do that is to label the most recent antecedent of that entity. There are also richer annotation schemes that allow coders to mark expletive, for example, or predicative noun phrases. And in standard anaphoric annotation projects, the mentions are predefined so that the coders can only focus on making anaphoric judgments and not on identifying correctly the mentions, which is a difficult task in itself, as at some point Chris might describe. He did some work on that. So here's an example of anaphoric annotation. Say we have this text: John, a colleague from work, said it will rain later today. He was right. So a good coder in this case should mark John as discuss new, because it introduces into this discourse, this entity about John. A colleague from work, it's a predicative noun phrase. It's a non-referring expression, an expletive. And he is a discuss old mention. And John is the most recent antecedent of the entity that he refers to. And we say that John and he are an entity and they form a coreference chain. Right, so what is the challenge with this type of annotation? So on the surface, this looks like a classification task, but in standard classification tasks, the set of classes the coders can choose from is fixed. Whereas here, the set of classes depends on the mentions the coders annotate. So yes, there are some predetermined labels like discuss new, like expletive, but there are also, but for the cases, for the discuss old mentions, they need to specify the most recent antecedent of the entities, and that changes from mention to mention. So because the class space is not fixed, you cannot use directly standard models of annotation like the one I described previously. All right, so how we address this? we took the annotations and transformed them into mention pairs. So here is an example that transforms 3 annotations for the pronoun he in the text before. 2 annotations of the coders are correct and 1 of them is incorrect. From the 3 annotations, we can extract 2 mention pairs. Mention pair he and John, which we say is of type discourse old, and for which we have 2 positive judgments and 1 negative judgment. And another mention pair, assuming that the coder marked he as a discourse new, would be he discourse new, type discourse new, for which we have 2 negative judgments and 1 positive judgment. And the model called MPA, mention pair annotation model, this is a reference to the mention pair model originally proposed by Sun et al. The model takes the judgments and assumes they are produced as according to the sensitivity and the specificity of the coders. More formally, here's MPA's generative process. So the generative process of a model is the set of assumptions the model makes about the data, the way the data is being generated. So for every mention pair, we have an indicator that encodes whether the mention pair is correct or not. And if the mention pair is believed to be correct, then the binary judgments associated with the mention pair are assumed to be produced according to the coder's sensitivity for that type of mention pairs. Whereas if the mention pair is incorrect, then the binary judgments are modeled according to the specificity of the coders. A few observations about this model. You probably noticed that the coders have sensitivity and a specificity for different types of mention pairs. This allows the model to capture, for example, that it's probably easier for the coders to correctly identify when new mentions are introduced into the text versus to correctly identify the right antecedent of a discuss old mention, or that predicative noun phrases are harder for the coders to correctly identify. Another observation is that once we have fitted the model to the data, we can use the posterior of the mention pair indicators and assign each mention the most likely interpretation. And from the mention pairs, we can then build coreference chains by following the link path specified by the mention pairs. And we can also use the model in an analysis of anaphoric ambiguity. We can identify the mentions that have more than 1 correct interpretations according to the model. And Alexandru and Massimo actually did some work in this sense. We used the model to aggregate the anaphoric interpretations collected by the phrase detectives game with a purpose. We released the corpus in 2019 with a paper at NACL. So the corpus back then had at least 8 anaphoric judgments for 100,000 mentions from 540 documents. And 45 of those documents were also annotated with labels from linguists. In terms of the performance of the model on the corpus, we can see that it does considerably better compared to a majority vote. Again, the main drawback of a majority vote is that it assumes all coders have the same ability. Notice also the differences in performance across the different types of mention pairs. This is in support of the decision to separate the ability of the coders across different types of mention pairs. As I said before, from the mention pairs, we can build coreference chains. And here we assess the quality of the coreference chains using standard coreference metrics. So the coreference chains would be the data that we need to feed to the coreference resolvers. And yeah, the same story as before. The chains produced using the MPA model are much better compared to those chains produced by majority voting, or the chains produced automatically by a rule-based system such as the Stanford system. After we did the work on coreference, we noticed that many other tasks in NLP do not adhere to the design of standard models of annotation. Standard models of annotation are mostly built for classification tasks, but there are many tasks where the annotations are somewhat different. For example, sequence labeling task is another example where the items have interdependencies, which are neglected by standard models of annotation. But you have many other examples from like preference labels, like machine translation task or mention identification. Based on this observation, we organized the workshop at TMNLP 2019, drawing the attention to the field on this subject, and also asking people to come up with solutions to aggregate annotations for different NLP tasks. This was done together with Dirk Hovey. More recently at EACL this year, we presented a tutorial that surveyed the literature on how you can aggregate the annotations for different NLP tasks, but also how you can train your machine learning models directly on the raw annotations, so without the aggregation. Finally, probably the most important work I've done, I helped writing a book on statistical methods for annotation analysis. This was together with Ron Arstein and with Massimo, a book that we just submitted last night. And this surveys the literature from the 60s to nowadays, discussing about coefficients of agreement, standard and probabilistic for reliability studies, discussing validity, discussing how you can aggregate annotations for all sorts of tasks when creating resources, but also various methods to train machine learning models on multi-annotated corpora. All right, thank you.
Thank you very much, Silviu. It was also perfectly timed, so lots of okay, so these are actually not the raised hands, these are claps. I was thinking, whoa, lots of questions, but yes, no. So, but are there any questions? Yes. Yeah, so we have, but yeah, we have a book to sell. So yes, if you
yes,
you can send your orders directly. Any questions? Okay, well, if there are no questions, I guess we can move on to Juntao. Okay.